Welcome to Menelaus Theorem. Woo!
Who was Menelaus? Menelaus of Alexandria. He was born about 70 AD in Alexandria, Egypt, shown in the picture right here. He was a great mathematician and astronomer who first conceived and defined a spherical triangle.
One of his major mathematical contributions was the formulation of the famous law of sines, which he proved on the surface of a sphere, which is two-dimensional, so when stretched out, it becomes a plane triangle. So that will give us A over sine of A equal to B over sine of B equal to C over sine of C. He is the first person to extensively study spherical trigonometry, including listing the 6 distinct cases of a right triangle in a spherical trigonometry. And he wrote 3 books on spherical trigonometry. His book 3 includes the theorem we are going to discuss today, Menelaus Theorem. If a straight line crosses the 3 sides of a triangle, one of the sides is extended beyond the vertices of the triangle. Then the product of the 3 of the non-adjacent line segments thus formed is equal to the product of the 3 remaining line segments of the triangle.
Thus, what Menelaus theorem says is the following. Given triangle ABC, the points PQR lie on the lines BC, CA, and AB, respectively. Assume that none of these points is a vertex of the triangle, then PQ and R are collinear. If and only if an even number of them lie on segments BC, CA, and AB, and AR over RB times BP over PC times CQ over QA equals 1.
But before we begin, let's talk about similarity. 2 geometric shapes are called similar if they are the same shape but not necessarily the same size. In the case of triangles, given triangle ABC and triangle XYZ, suppose that angle A is equal to angle X and angle B is equal to angle Y. Then, that would mean angle C would have to be equal to angle Z. The 2 triangles are similar if the 3 angles of one are equal to the 3 of the other triangle. So if 2 angles of a triangle are equal to the 2 angles of the other triangle, then the third angles are necessarily equal. Therefore, triangle ABC is similar to triangle XYZ. And this symbol right here, it just means similar.
The second topic to know before we prove the Menelaus theorem is the area. As we all know, the area of a rectangle is base times height. And when we cut this rectangle in half, we get a triangle. Then we can say that the triangle ABC has the area of 1/2 times the height AB times BC, the base.
So, given triangle ABC, we'll draw a line from B onto the base AC and call that point D. Triangle ABD, the area of triangle ABD will have half of its base AD times the height. Triangle BDC will have the area of half its base, DC, times the height. They share the same height. Crazy! Thus, the height is equal to 2 of the area ABD divided by its base AD. And the height is also 2 of the area of triangle BDC divided by its base DC. These heights are equal. So That implies that you can cancel out the 2's and get the area of ABD over area of BDC will equal to AD over DC.
The subtraction principle for ratios. What are ratios? Ratio is a statement of how two numbers compare, like 1/2 is less than 3/4. And this principle says, let's say we have equivalent ratios, A over B and C over D. Then, by this principle, the difference between them is also equal to the ratios, as known as A over B equals C over D equals A minus C over B minus D. Of course, B minus D cannot equal to 0. How does this work? Let's say S is equal to these equivalent ratios. Then, when we rearrange these equations, we get A equals S times B and C equals S times D. Then we subtract A minus C. A minus C is equal to S times B minus D. Then we solve for S. S is equal to A minus C over B minus C, which is equal to A minus A over D and C over D. Now we're going to look at Cheva's theorem. The original Menelaus theorem was proven a little differently than our proof. We're going to use Cheva's theorem to prove the Menelaus theorem. Giovanni Ceva was born in early 17th century and proved his theorem in 1678. However, King of Zaragoza, Spain, Yusuf al-Mu'taman, he proved this theorem much earlier than Ceva in the 11th century. Now we're going to look at the theorem. Given triangle ABC, we're going to draw lines from the vertices onto the opposite sides. AP, BQ, and CR. These lines are called Chevians. Chevian, by definition, is any line segment from any vertex of a triangle that cuts across the interior of a triangle and lie on the opposite sides of the triangle, as shown in the picture. It can also join a vertex of a triangle to a point on an extension of the opposite side. And these are concurrent if and only if AR over RB times BP over PC times CQ over QA equals 1. And this product is called the Chevian product. Now let's prove Cheva's theorem. Given triangle ABC and its Chevians AP, BQ, and CR, consider triangle ABP and triangle APC. They have bases BP and PC, and they have equal heights. Therefore, BP over PC is the ratio of the areas of triangle ABP and triangle APC. We're going to call the intersection of all Chevians point T. And consider triangle BTP and triangle CTP. They also have bases BP and PC, and they have equal heights. Therefore, BP over PC is the ratio of the areas of triangle BTP and triangle CTP. So BP over PC is equal to the area of ABP over area of APC, which is also equal to the area of BTP over area of CTP. With this equation, using subtraction principle for ratios that we discussed earlier, BP over PC is equal to the area of ABP minus area of BTP over area of APC minus area of CTP, which is equal to the area of ABT over area of CAT. Similarly, AR over RB is equal to the area of CAT over area of BCT. And CQ over QA is equal to the area of BCT over area of ABT. Therefore, AR over RB times BP over PC times CQ over QA is equal to the area of CAT over area of BCT times area of ABT over area of CAT times area of BCT over area of ABT. Then we notice that we can cancel all terms out. And it gives us 1, proving the Cheva's theorem. And Cheva's theorem's converse is also true by proving the method of contradiction. Finally, the proof of Menelaus theorem. Since Menelaus theorem is a biconditional statement, known as if and only if statement, we have to prove both the conditional and the converse statements. First, we're going to look at the conditional statement. It says, if P, Q, and R are collinear, meaning that they lie on the same line, then an even number of them lie on segments BC, CA, and AB. And our Chevian product is equal to 1. Now draw AP and CR as shown in the figures on the left and work with both diagrams. With both diagrams, let's consider triangle BPR and triangle CPR. They have BP and PC as their bases. They have equal heights. Thus, BP over PC is equal to the area of BPR over area of CPR. Similarly, triangle APR and triangle BPR have the bases AR and RB. We get AR over RB equals area of APR over area of BPR. I'm going to calculate the ratio CQ over QA twice. Using triangle CQP and triangle AQP, CQ over QA is equal to the area of CQP over area of AQP. Similarly, using triangle CQR and triangle AQR, CQ over QA is equal to the area of CQR over area of AQR. Therefore, this equation holds. Now we know that CQ over QA is equal to the area of CQP over the area of AQP, which is also equal to the area of CQR over area of AQR. By using subtraction principle for ratios, we can say CQ over QA is equal to the area of CQP minus the area of CQR over the area of AQP minus the area of AQR, which results in the area of CPR over the area of APR. Everything now cancels when we compute the Chevian product. cancel, another cancel. So we get the product equal to 1 as desired. The converse of the Menelaus theorem say, if an even number of points P, Q, and R are lying on segments BC, CA, and AB, and the Chevian product is equal to 1, then P, Q, and R are collinear. Simply stating that the Chevian product is equal to 1, with P, Q, and R really lie on the same line. Assume that the Chevian product equals to 1. Then now let's connect R and Q, and we're going to call the intersection of RQ and BC P prime. Is P prime equal to P? Using Cheva's theorem, we know that this product with P prime equals to 1. So we can say that this equation, this product, is equal to the original product with P in it, since they are both equal to 1. We can cancel things on both sides and get BP prime over P prime C equals BP over PC. Then we're going to add 1 to both sides. That results in BP prime plus P prime C all over P prime C equals BP plus PC over PC. Notice in the picture, BP prime plus P prime C is equal to BC, which is also equal to BP plus PC. So we can replace the numerators with BC. Then we get P prime C equals PC. Therefore, P prime is equal to P as desired.
Another proof for the Menelaus theorem is that given triangle A, B, C, and a collinear line XYZ on the triangle, and dropping perpendicular lines from each vertex to the line XYZ will give you heights. The height of A onto point M, the height of B touching point N, and the height of C touching point O. Labeling each height as HA, HB, and HC as we saw to the corresponding vertices, and comparing triangle ZAM and triangle ZCO for similarity. As we can see that these two triangles have a similar angle, or have a common angle Z and one perpendicular angle, which makes them similar. This will imply the equation AZ over CZ equal to the height of A over height of C. Now we're going to do the same thing with two different pairs of triangles. So we compare triangle BXN with triangle CXO for similarity, and also triangle AYM with triangle BYN for similarity. They will each have a vertical angle with one perpendicular angle, and that will automatically make them both similar to their corresponding triangles. You will get the same equation, and multiplying all three equations together will give us triangle AZ over CZ multiplied by BX over CX multiplied by BY over AY equal to the height of A over height of C times height of C over height of B times height of B over height of A. Now the entire right side of the equation can cancel out, leaving us with 1. Thank you, Professor Akbar.
And our textbook geometry for college students. Woo!